Good evening, everyone. Um, so, today is the live session number 8 for the course Affective Computing. I welcome you all for those who are watching the video. In this week, we have to cover this topic related to multimodal emotion recognition. So, basically, till now, we saw how we can detect emotions or um, detect the underlying emotion or affective states using different modalities. We talked about physiological signals, we talked about the facial expressions, we talked about sound, I mean voice, and so on. Is there any way of using all of these modalities together? So we can do that using by designing multimodal systems. Now, what are multimodal systems? How can we use them? What are the limitations? What are the things that you need to take care? We will cover in this week 8 session. So, as you know, in this session, we are going to solve some problems from the previous year assignment from 2024, 2023, and some extra questions. So, I'm starting with question number 1. So, I would highly suggest you all to just pause the question for a while, pause the video for a while, and then try to answer. Okay, so which statement best describes the expectation of a multimodal emotion recognition system? Each modality is anticipated to offer redundant information. Each modality is expected to provide unique information. Combining modalities is unnecessary for accurate emotion recognition. Modality combination diminishes the effectiveness of emotion recognition. So, what exactly is multimodal emotion recognition? Uh, it refers to the process of it refers to the process of identifying and interpreting human emotions by combining information from multiple sources, multiple sensory sources or modalities. So rather than relying on just one kind of data, let's say only facial expressions, we want to combine information from multiple sources, such as facial expressions and voice and maybe physiological signals, let's say EEG. So, multimodal systems leverage multiple channels, let's say, as I mentioned, facial expressions, voice tone, body language, text, even the transcript can be used, physiological signals, and heart rate or skin conductance, EEG, galvanic skin response, etc., to more accurately assess and recognize a person's emotional state. So, why multimodal emotion recognition? As we just discussed that, but why do we actually need it? So what happens is emotions are complex, so and people express them in different ways. It's not always the case if I'm smiling that means I'm happy. I might be um, faking the smile. So and you can sense the sadness in my voice maybe, but not in my expressions. So if I use only my facial expressions, it is not that reliable. So we want to combine information from the voice as well, let's say in my case. So yeah, for example, facial expressions can be sometimes misleading because we can fake those expressions. Okay, someone might smile but they can be nervous. Let's say in an interview you feel nervous but you're still smiling. Voice tone alone might not provide enough context. Voice tone can provide us it is involuntary, so it is a kind of better approximation of what emotion you are feeling, but still we need more context. So someone, a monotone voice might not reveal excitement or so. And then physiological signals can reveal stress or relaxation, like they can tell us about arousal state. However, the positive and negative aspect, that is the valence, they cannot tell. So it's So it's better that we use a combination of all these modalities, let's say, and we design the systems in such a way that from each modality we are getting some um, other, like, complementary information, and the information is not redundant. So this is an example of multimodal emotion recognition system. uh, if you see here, we have a video clip. In video clip, and video clip is being shown, this is the stimulus and this is the recording of the person watching it. So we have the video data, and there are sensors. If you look closely, there are electrodes. So basically they have also collected the EEG data through EEG cap. Now we have the EEG data as well as visual data. So how can we use this in combination? So we can somehow combine the information and then train a model, or maybe decision level fusion, early fusion. We will talk about these fusion techniques in coming slides. So but anyways, the motive is to combine the information from both the modalities. So this is a kind of a typical pipeline. Now, in multimodal systems, each modality each modality is anticipated to contribute unique information. It shouldn't be the case that you're getting the same information from text, you're getting the same information from your voice, and it shouldn't be the case, because we expect that these modalities will carry some complementary information. So let's say facial expressions might reveal immediate emotional reactions, while voice intonation can provide cues about the intensity, right? And physiological signals can offer insight into stress or arousal levels. So while there are many, of course there will be some redundant information, but then the primary goal is combining to capture different aspects, and complementary information. Although there will be redundancy as well, we cannot avoid the redundancy, because ultimately they are interconnected, right? If I'm happy, so everything will be according to that state. So yeah, it helps us to improve accuracy, robustness, overall emotion detection, especially in the cases where one modality can be ambiguous or missing. Let's say if you just read out a sentence in the transcript, you might not get how the person might have spoken it. Let's say there is a neutral sentence. Um, did I ask you this? So if you just read it out, then you don't know what was the tone, what was the intention of the person. So the question was, which best describes the expectations of a multimodal emotion recognition system. So each modality is expected to provide unique information, okay? And we do not want any redundant information. I mean, we want to avoid it as much as possible. Okay, next question is, if any two modalities convey identical emotional information, combining them may increase computational load without improving system performance. So, when we combine multimodal information, and if the information is redundant, let's say my facial expressions and the uh, some other, let's say EEG, they're not providing some complementary information, and the information is quite redundant, then we are essentially processing the same information twice. So sorry, so we are processing the same information twice, which does not add any new insights. But of course we need to process the both the modalities, so we need additional computational resources, and it's just a waste of time and computational resources. So let's say both the modalities are more accurate measures of arousal and not valence. That means adding both will not improve the accuracy, because ultimately the only information that you know is arousal, and you still don't know the cues about the valence part. So it is not going to improve the system. Let's say text and facial expressions, and they cannot they cannot estimate the arousal. Okay, so let me just okay, so they cannot estimate the arousal state. So combining text and facial expressions might be redundant and just the waste of computational resources. Okay, what is the primary challenge in early feature fusion of different modalities? Synchronization issues, difficulty in selecting the appropriate ML algorithm leads to an increase in computational complexity, lack of available datasets. So, if we talk about different fusion strategies, till now we have talked about that we need to or we want to combine different modalities to obtain different information, complementary information. But how can we combine this information? So there are a few strategies. Most commonly, there are three most common strategies. One is early fusion, second is late fusion, and the third one is intermediate fusion. So, in early fusion, as the name suggests, we start early in the pipeline. So, deep learning systems usually. So, we have this data, and let's say this is EEG, and usually, let's say only one modality is there. We will feed it to some model, right? And it will just give us a decision. Okay, now let's say we want to add uh, facial expressions data. So this is, let's say, visual data. So how are we going to combine it? Are we going to use the same model or are we going to use a different model? So it entirely depends on what technique you are going to use. So if you choose the early fusion method, then we extract the features and we use the same model to train the uh, to train on the data. So let's say I'll draw something here. So hello, thanks for joining the session. So currently I was discussing about early fusion method. So the current discussion is about the multimodal emotion recognition systems. So we are just talking about how what are the different methods to combine the information from different modalities. Now, so the first method is early fusion, and for early fusion, what we need to do is, let's say this is my features from EEG, and let's say these are my features from visual data, that is the video. Then if I want to combine them, so I can, let's say I can concatenate them. uh, let's say I want to concat the information. So now it becomes a combined feature. We can use multiple strategies, but this is the simplest one. We can use a combination of the features and then we can feed this to the model and we can train the model according to this combined features using these combined features. So okay, early fusion is a technique where data or features from different modalities are combined at the initial stages of the process. That's why we call it as early fusion. Now, before the classification or decision making step. So, this fusion occurs as at the feature level. It is also called feature fusion. Okay, so raw data or lower level features from each modality are merged and then they passed they are passed through a unified model or pipeline for further analysis. So what we do is merge real data or features. So it involves taking features from multiple modalities and combining them into a single unified feature vector. And this is occurring before the model training or before the deep learning part is there going on. So let's say you're combining audio and visual data. So early fusion would involve concatenating those features, okay, and such as voice, pitch, or facial landmarks, so into a single input vector. Now processing unified features, we train our model to take the information from both the modalities, and then a neural network or a classifier, it is trained on the joint analysis, and it learns from the correlation between features. Let's say I'm smiling, and I my EEG signal will also show something related to happiness. That means some kind of correlation is there. Okay, so let's say if I'm feeling happy, then my facial expression would most likely be smile on my face, and also my, let's say, a specific region of my brain will be activated. So this model, what it does is it will find patterns, that whenever you're like smiling, or whenever the person is experiencing happiness, then you are uh, experiencing this smile on your face, as well as the certain region is being activated. So yeah, so it identifies the patterns or the correlations between different modalities, and simultaneous learning is happening. So it allows the model to learn the relationships between the modalities early in the process. Let's say someone smiles, and might correlate with the tone of voice, okay, that the tone is also changed. If a person is sad, then the pitch is, let's say, more on the lower side, and the voice becomes more heavier. And if you're happy and excited, then the voice becomes more shriller. So early fusion helps us to detect these kind of patterns. So what are the advantages? We are able to figure out the cross modality information, right? And then it is a more of a integrated representations. It gives a more comprehensive view of the raw data. By fusing these different feature sets early on, the system can make more holistic and context aware predictions. What is happening in, like, visually and auditory perception, so it can just look and figure out patterns. Now it also simplifies a system architecture, because we essentially need the combination here somewhere, okay, and then the same pipeline, it becomes it becomes like a simple pipeline only. Just one model is required, and the training is happening, and then it learns everything, right? So simple pipeline, just the modalities are being combined. Okay, then, but the disadvantages are also there. So disadvantages include the dimensionality and complexity. See, uh, if there are three modalities I'm combining, so earlier I only had this, let's say, 512 dimensional vector. Now I also have, in addition to this, I also have another, let's say, 256 dimensional, and let's say the third modality is represented using this color. So let's say this is also 1024. So the now the dimension of the data, it has increased significantly. So the dimensionality, it leads to very large feature vectors, and it is difficult to process because the computational requirements are also increased now. So increases the computational complexity and requirements. Also, whenever the data is high dimension, we require more data points, because I mean, if otherwise it would lead to overfitting, okay. Yeah, it can also slow down training and require significant computational resources. Now also, one of the major drawbacks is difficulty in synchronization. So synchronization is what, between these modalities, between 1, 2 and 3 modalities, if we want to check, like okay, these features, let's say they belong to the whole video, but let's say this is the video going on 1 frame, 2 frame, but the audio is continuous, so sampling rate of audio is very on the higher side. So how are we going to actually compare that? Let's say I have 10 data points for one modality, or 100 data points for the other modality. So how are we going to map those labels, or map those points to each other, that okay, during let's say 10 seconds, what was exactly the state of your EEG signals or your facial expression? So we need to align and synchronize these modalities information that they carry. It is a tedious task. So let's say another example is, if the modalities operate on different time scales or have different sample rates. Let's say the video frames are 30 fps, but audio can be 16 kilohertz. So how are you going to map the 16 kilohertz to 30 fps? This becomes a difficult problem. Now let's say the speech features are extracted per second and the video frames are extracted per millisecond. So aligning these features is also a difficult task. Also, the noise amplification is there. So what exactly is noise amplification? That means if one modality is noisy or redundant or unreliable, so it is, let's say, poor quality audio. My audio was not that clear, and I my EEG signals were very clear. Now I have, by combining the information, I have downgraded the quality that alone EEG signal would provide me. So it, combining it with the clean features from other modality early in the process, it could degrade overall performance. So the noise from one modality could negatively affect the combined feature vector. Okay, so main challenge is, again, as I mentioned, it is the synchronization. uh okay, so different modalities have different feature dimensions. Let's say audio features have different dimensions compared to the image features. So these are MFCCs and these are pixel intensities. So the range is also different. How are we going to combine the information? Now different temporal resolutions, different rates or different sampling rates are there. Synchronization is then difficult. Incompatible feature spaces. One is like text. One is the text modality, which represents the linguistic information, and one is the let's say image features. They're more on the spatial side. Spatial and linguistic are two different things, and we cannot just like put them together and just feed to the model, because we need to make sure key whatever we are combining, it should make sense to you. Okay, it should be meaningful. Now just to summarize the process, these are the few strategies to combine. So we have talked about early fusion. In the coming slides we will talk about late fusion and slow fusion as well. So I hope the early fusion is clear, and let's go through it one more time. So we have these features, and we are just like, we have these modalities, and we are, let's say, combining these modalities or features. So it becomes a single pipeline, like the single model is being trained, and it gives us the final decision after that here. Okay, um okay, so yeah, the primary challenge becomes synchronization issues due to differences in feature dimensions. Yes, this is true. Difficulties in selecting the appropriate ML algorithm. No, ML algorithm is totally your choice, like whatever algorithm do you want to use. So this is false. Then it leads to an increase in computational complexity. Of course, early fusion, any fusion technique for that matter, it will increase the computational complexity, but it is not the primary challenge associated with the early feature fusion. Okay, and lack of available data sets. No, this is also not true, because early fusion is nothing like, it is just combining, and it is not your headache to like the data sets itself are already there. We don't need a special data set for early fusion. So yeah, combination experiment, we just need individual data sets, and then we can combine. Let's say obviously, like multi-model data sets are like lesser than the single modality, but then again, if we are using some fusion techniques, then there must be some data set that we are using. Okay, which of the following is not a technique used for combining outputs in late fusion? um, this is averaging, early fusion, voting, or all of the above. So late fusion, we just talked about early fusion. Now what is late fusion? Late fusion is a technique which is used in multimodal systems when we are like processing different modalities separately. So let's say we have audio, video, and text, and then when are we combining? So we are, let's say, three different modalities. So this is the text, this is the visual video, or this is the audio. Okay, now this will be passed through a different model, like this is will model 1, model 2, model 3. It will give you some kind of output. Okay, now we have different methods to uh, combine these. Let's say my task is emotion recognition, right? So I need to tell if the person is happy or sad. Now you use these models to predict some value. Let's say this model tells you it is happy, then this model also tells you it's happy, but this tells you it's sad. That means, how are you going to assign the final label? So final label will be a combination of these, happy and sad. So what mechanisms can we use to make the final decision or final label? So we'll read this out. um, but firstly, I hope you got the idea. It is independently processing each modality. So each modality is processed separately using its own model method, and then at the end, when we have the predictions from the some scores or some predictions from different models or different modalities, then we take those output numbers and then somehow combine. Now the output from each modality can be a score, a classification label, or a confidence level regarding the emotional state, user intention, other criteria, whatever. Now how do we combine? We somehow combine to arrive at a final decision. This combination can be using averaging, voting, or weighted combination. We will just talk about it in a while. Now final decision, it is based on collective information from all the modalities. So we are essentially combining, but at the later stage. This is at a later stage. So that is why we call it late fusion. Okay, now what are the advantages? Modality independence, like it is processed independently. Let's say there is a model which is very good for audio processing. Now you can use that model for audio processing. Let's say there another model is for EEG signals, it is already there. You can use the pre-trained model for EEG pipeline. Then finally, when you arrive at some result, then you can combine. So also, let's say one modality is unavailable. Let's say your data was corrupted and the EEG signal did not record well. Now you can skip that part and just use the other two modalities. So it gives you more flexibility. So one modality is unavailable, then the system will still function. It won't. But in the case of early fusion, if one modality is missing because the model needs anyhow it needs the data from all the modalities that it is trained on, then it won't work. So it gives you, late fusion gives you more flexibility over early fusion. Also, we do not need to synchronize these things. Let's say different sample rates are there and different characteristics are there. Different models are handling the data separately. After every processing has happened, then we are combining. So we do not need to synchronize. There is no need to synchronize the features. Okay. Then, but the disadvantage is, the advantage that early fusion offers is we know the relationship between, correlation between the different modalities. However, since we are not synchronizing, since we are not letting them communicate with each other, then potential correlations between the modalities we cannot judge. Let's say you are happy, so your intonation will be, as I mentioned, pitch will be high. But and if you're talking with a smile on and your pitch is high, that means matlab happiness ko, it belong, these features belong to happiness. So, but in this case, since it is independently being processed, there is no communication at all between the two modalities. So limited even potential loss of cross modality information, and integration is also limited. So it is independently informative, but it might not fully exploit the rich or complementary information that can be found across the modalities. So first method is averaging. Averaging comes into picture when different models are giving us some kind of score or probability or a number, right? So it is a widely used technique. And let's say if two modalities are giving confidence score for an emotion, let's say sadness is detected with zero point 0.7 probability from facial expressions and zero point 0.8 from speech analysis. So the average will be 0.75. So if it is greater than, let's say 0.75 is greater than zero point 0.5, so I will assign it sadness. ठीक है. So it is better than chance level, so we are going to assign the label sadness. Similarly, it is very simple technique, right? It is very simple and it balances out. If one modality is telling you something and other is also providing some information, you take some information from both and average it. Weakness is, it tells you that all the modalities are equally important, and it does not account for modality specific reliability. Let's say your audio was not good, now it is still, you process it and there is a lot of noise and it gives you some kind of score, let's say zero point 0.8 for happiness, whereas the actual label is sadness. So but let's say the facial expression, it is giving the probability. Let's say facial expressions gives you zero point 0.9, but audio gives you 0.2, just because it was corrupted. Now the overall score, so it becomes, right, so it becomes like that. It drops down from this to this. So this modality, adding this modality, dropped the overall score from zero point 0.9 to 0.5. So this impacted it badly, it made it worse. So yeah, but like we are not giving us any we are not giving it any weightage. We should give some weightage to the modality which is more reliable. In our case, let's say these facial expressions are more reliable, so it's better to give them more of a weight or weightage. Okay, so another method is voting. Voting is very straightforward. Like if two modalities are saying majority voting basically. So if two modalities out of three, they are saying that this is happy, then assign happiness. So let's say facial expression detector predicts happiness, speech based emotion says it's sad, and physiological suggests happiness. So majority, 2 out of 3 are saying happiness, so happiness would be selected. And it is strengths are like in the previous example, the audio modality did not contribute much, even it made it worse. But in this case, if you take the majority, let's say there are other modalities as well, so it is robust to noise. If one modality is somehow corrupted and it is giving you the wrong result, but majority are giving you the right one, so as right label will be assigned. So weakness is it might overlook the other information. Let's say you don't know how confident the model was. Let's say you're trusting the facial expressions, or you're trusting the every model blindly, but let's say they are not even that strong, they're all giving you some wrong labels, although they are in majority, but they're wrong. So you do not know how much reliable your model is. Okay, so which is not a technique. We know that averaging is a technique, then voting is also a technique, but early fusion is actually not a late fusion. How can early fusion be a late fusion technique anyways? Okay, now soft late fusion. Now soft late fusion involves incorporating a measure of confidence which is linked to the decisions being made, true or false. So, in the soft late fusion method, it is a method which is used in multimodal systems. Uh, let's say where the outputs predictions are of different modalities are combined to make a final decision. We know that. Now, how is it different from late fusion? Um, from regular late fusion is that it incorporates a measure of confidence or reliability. So you can think of this as something like weighted average. Okay, something like weighted average. You are giving weight to, let's say your camera is very good but your mic was not good, so you can say that my audio is not that reliable and my visuals are more reliable. So you can give this more weightage, let's say zero point 0.8 weightage to visuals, 0.1 to audio, and 0.1 to EEG, let's say. Okay, so whenever, let's say, this visual model is telling you that I predict happiness, and with a score of zero point 0.7, or audio is saying I predict sadness, and this is also saying, let's say, happiness with a lower score. This is 7. So how are we going to combine the information? uh, Actually this should be sadness, sorry, happiness. And so this is giving you zero point 0.2. So now if you directly take the average, it will be very low. How and But we are, since we are giving the priority to this, so if I choose to combine this, I can say zero point 0.8 multiply by zero point 0.7 plus zero point 0.1 multiply by zero point 0.2 plus 0.1 multiply by zero point 0.3, something like this. Like, this is the weights and this is the probability, so weight into probability. So this is w1 p1, w2 p2, w3 p3, and so on. So now it counters the bad modality so that it does not make it worse. Now there can be techniques like confidence. This is a confidence based weightage. So each modality's output is weighted and based on the confidence level. Also, this has adaptive influence. The confidence can be changed. It's not like that you have fixed the zero point 0.8 for facial expressions. It will see the performance of each modality on specific tasks, on real performance tasks, so it is more adaptable and it adds to the robustness of the system. Now there is an example. Let's say facial expression, speech and heart rate variability. So facial expressions detects with 90% confidence, speech detects with 70%, and this indicates excitement but with only 50% confidence. So in soft late fusion, what we can do, give more weightage to the facial expressions because it is more confident. This is more confident, and slightly less confident, and then this is not that confident, this is very confused. Then the heart rate analysis would have the less influence. Okay, so again, it is just the weighted summation or weighted average, you can say. Okay, having overlapping information can lead to the curse of dimensionality, particularly in scenarios like feature fusion where overlap is common. True or false? So if we talk about the curse of dimensionality, now what exactly is the curse of dimensionality? um, it refers to the challenges and complications that arise when working with high dimensional data. See, increasing the dimensions, it can help us to certain extent to get more information from the, to extract more information. Let's say if I only use 2 bits to represent data, only a few numbers can be represented, but if I use 8 bits, then more combinations are possible, and it will give me a more sample space, right? Similarly, if we talk about these feature dimensions, if I increase the number of feature dimensions, maybe it will be able to capture more information. Let's say initially I had only uh, let's say 64 dimensional, and now I increase to 256 dimension. Of course, this will carry more information. Okay, so we are actually giving it a chance to learn more information. But if we keep on increasing and being greedy and keep on increasing the dimensions, it is not always the case that it will perform good only. But the bad part is that we need something more resources to handle these high dimensional data. So um, as the dimensionality increases, the amount of data needed is also increased. uh, this is something related to the data sparsity problem. Like in higher dimensional spaces, data points become sparse, and it becomes difficult to find patterns, detect meaningful patterns, because the data doesn't fill specifically. Let's say if on 1D or 2D, let's say this is 2D and there are 2 points or 3 points, but if I plot a 3D, then one point is lying there, one is lying there, and so it becomes more sparse. This is more dense. So you can see the clustering kind of, it is not being able to find some patterns, although in 2D it is more of a clustered thing. Similarly, in this context, uh, the ML models will find it difficult to learn the relationships between the features if the dimension is very very high. Also, we have increased computational cost, and it needs more processing power, more storage requirements are there. Then overfitting is also there. In high dimensional spaces, models, they tend to memorize the training data and do not generalize well to the new data, which is the test data. So if too many features are fed, it focuses on the unnecessary information and making it um, more like useless information is being learned instead of paying attention to the most important features. So it might learn noise and rather than the underlying pattern. So overfitting is also uh, caused by this curse of, I mean, if you just increase the dimensionality, so that is the curse. Now feature fusion and curse of dimensionality, how are these two related? When we combine multiple features, we saw that the dimension will increase, and if it is redundant, then there is no point of increasing the feature dimension, because ultimately it's going to be a waste of resources without any improvements. um, and let's say both facial expressions and vocal tones are just indicating excitement, and we do not know the valence. The arousal part is there, but the balance is not there. So feature spaces grow larger, but some features are not adding new information due to overlap because they carry the similar information. So it increases the data size, the feature size, and ultimately converts into the contributes to the curse of dimensionality. So the previous thing that we discussed, these will be a part of um, your like system if you do not use, or if you do not increase the features more mindfully. So we need to combine some modalities in such a way that they carry complementary information and not the existing information or redundant information. Okay, what assumption is made in decision level fusion? We know decision level means, this means late fusion, just the other name, because ultimately at the time of decision we are fusing the different weightages or different predictions from the different models. So for this we assume that there is conditional independence. Now what is conditional independence? It means that the decisions made by each modality are assumed to be independent of each other, but this is not saying that they're not even related. They are related. Let's say you know that this is happiness, and you see smile and a shriller pitch. So then you will be able to correlate that, okay, if I'm seeing the happiness, and then if a person is smiling and the pitch is also behaving in a certain way, then you can obtain some patterns from that. But does not mean that one thing influences other. So the most important thing to note here is the predictions made by each modality do not influence each other, and it simplifies the problem because it allows different modalities to provide complementary information or even redundant without explicitly considering how the decisions from one modality is affecting the others. Some interdependence is always there. um, some redundant information is always there, but assuming this independence, that my facial expression has not nothing, I mean I can process it alone without my voice, so they are kind of independent of each other. But again, they're not unrelated, but they are independent, which we can process it independently. So parallel or asynchronously they can be processed. Now an example would be a person is speaking in cheerful or excited tone, and facial expression says the person is smiling. And if we assume complete independence means there is absolutely no relation, then it would say speech and facial expressions are completely unrelated, but which is not the case, right? Even if uh, they both clearly indicate happiness, so of course they are related. And conditional independence gives you this benefit, that it tells you that the system can treat and like speech and the facial expressions conditionally independent, because once we know it's happiness, we can separately analyze both the modalities. Happy tone confirms happiness, smiling also confirms happiness. So if we treat them conditionally independent, then the system can combine the two decisions to just to keep, like let's say take voting or averaging, to reinforce the idea that emotion is happiness without worrying about whether are related in every situation or not. Okay, in this particular situation we are concerned about, so that is confirmed here. So the answer is conditional independence between modalities. Then comes slow fusion, provides us with correlation between modalities while relaxing the requirement of synchronization. So slow fusion is the third technique that we are about to discuss. So slow fusion, what exactly is a slow fusion? It is a method which is used for this multimodal fusion, and it is different from early fusion as and late fusion. In early fusion, we are just combining the features. In late fusion, we are combining the decisions. However, in slow fusion, it is more of an intermediate fusion technique. It combines processes and combines the features gradually over time rather than a single point. Okay, it involves processing each modality into a latent representation, fusing them, and then doing exact like final processing to produce the output scores. The exact okay, how we combine in the intermediate states, it depends on whatever you want to do. It is more of an implementation concept. However, let's say you want to say concatenation, or if the dimensions are same, you can also add them, or even attention mechanisms are can also be used to make sure that only the uh, relevant information is captured from the cross modality. So the advantage is it is able to learn rich interactions between each modality because they are first converted to a machine understandable representation. So let's see with the help of an, I think diagram is also there later somewhere. So correlation between modalities, in slow fusion we are able to, since we are like capturing it at, hi Dhanya, do you have any questions? uh Dhanya, if you have any questions. I think, okay. Okay, okay, no worries, no worries. Okay, thank you just for listening, even if you're listening. Um, then it's great. Okay, so I was talking about the, we are able to capture the correlation between modalities. In slow fusion, we combine from different sources at early stage, and but then at different stages within the pipeline. Throughout the process, it is happening, not on either extreme. Okay, so we are able to capture and leverage the correlation between these modalities in a more detailed manner. So in video and speech, for example, both evolve over time, and slow fusion it captures these dynamic changes. And also we do not need to synchronize it end to end properly. What we can do is, it is more of a relaxed synchronization. It has more relaxed synchronization requirements. That means it, since it integrates modalities gradually, so we can just rely on, we don't need any strict synchronization between them. Okay, so perfect synchronization is also very difficult to obtain. And it slow fusion gives us more flexible, uh, you know more flexible way of doing that, since we saw that early fusion has this disadvantage that we need more strict synchronization policies. So it provides us with a correlation which is true. Okay, what when performing decision level fusion or late fusion, what potential loss of information could occur? Loss of computational efficiency, loss of model interpretability, loss of correlation between individual features, or feature diversity. So we have just discussed this, that if we just combine the decisions, we don't know how the features are going to be correlated with each other. So the answer is loss of correlation. But let's read this out. um, we know that late fusion has certain disadvantages. Let's say, um, it the major, again the major is the loss of correlation. It just processes every modality independently and then combines the final outputs or the probabilities or the and it does not capture the interdependency or the correlation between the features or different modalities. And let's say facial expressions, vocal tone, and emotion recognition is like very evident if you look at the facial expressions and vocal tone together. Because um, if like a person is shouting, let's say, in more aggressive manner, so you can observe that the facial expression, face becomes more red, expressions are more like lips are more lifted and so on. um, and the tone becomes more sharp, shriller. So they're correlated somehow. If we just use the decision level, you won't be able to capture these nuances. However, if you use early fusion or slow fusion, then you will be able to capture these patterns. So the answer is loss of correlation between individual features. Okay, next question is, SVM is an example of which fusion technique? Uh, SVM. SVM is not even a fusion technique. SVM is a classifier, right? So it is more of a ML classifier. It's a machine learning algorithm. It is not a feature fusion technique exactly, but it can use like multiple features which are combined early. Okay, so maybe facial features, or maybe some, uh, you can say, my audio features, voice features. So you can earlier provide them together. Let's say my facial landmarks. Okay, facial landmark AU. If you remember AU's action unit information, so you can provide like AU1, AU2, something like that. We have some features, and then also this belongs to the video modality, and I can also, for the audio part, I can also provide MFCC coefficient 1, coefficient 2, like that. So already I have this some data which is already having multiple modalities in it. So uh, but here we are providing it at an early stage, not the decision level. It doesn't make sense in this case. So in SVM we essentially combine the features early. So if the question was what kind of fusion technique does SVM support, or SVM does, I think it should be early fusion. And but SVM itself is not a, it is not a fusion technique. It is a classifier. It is an ML algorithm. Okay, next question is, combining multiple modalities always ensures more accurate inference and expression. Is it always the case that if you combine multiple modalities, you're going to get performance enhancement? It is false. Why? Is it the case more the merrier? Because it can potentially enhance. Potentially is the keyword here. Maybe. We're not sure that adding the audio modality will give me better results, because in the other example also we saw that the audio was, let's say, corrupted. Now you are using a corrupted audio to, spoil the existing methods, existing good results you're having just by using the facial expressions, which is like, let's say, very clear. You are able to capture everything very clearly, nicely. You're getting some good results. However, if you add the voice as well, and the quality is not good, the model will be more confused. Instead of improving the performance, it can downgrade the performance. So it depends on various factors: the quality of the data, the choice of fusion techniques, the complexity of the affective states. If it is straightforward, then maybe not a problem, but if it is more complex, then you need uh, more modalities, or even less modalities. It can also be the opposite. Also, in some cases, some modalities can introduce noise or irrelevant information or redundant information, which might lead to decreased accuracy, and when combined with others, okay, it can improper fusion methods or mismatches. Let's say you're not even synchronizing it well, and you're using early fusion. You're just concatenating the features, but then two modalities have different sampling rates, different sources of data. They're not even aligned in the time domain. So how can you just concatenate everything? You need to have a more aligned data. So it can also hinder accuracy, because ultimately you're spoiling the existing data. Now, yeah, so the crux is that it's not always the case that if you add more and more and more data, it will increase the performance. So adding new modalities might decrease the performance as well. Okay. Yeah, might is the keyword, because you cannot just state something that it is going to increase. It might, or might not for that matter. Okay, which of the following is not a righteous feature fusion technique? Um Earlier fusion, late fusion, decision fusion, or selective fusion? So we have discussed about the early fusion technique, which is known as the feature fusion, feature level fusion, right? And we saw that, I see Vishesh has joined right now, so I'll just briefly go through it over once again. So mostly we are talking about the multi-model emotion recognition today, and we have discussed about a few techniques. There are mainly three fusion techniques, when you can combine, using which you can combine different modalities. Let's say you have text data, the transcript, you have the voice of the person, and you have facial expressions. So what you can do is, you can combine the information from these modalities and then predict, and the intention is to design models which are having enhanced performance. However, it might not be the case always that it might increase the performance, it might also decrease. Now the techniques are early fusion. Early fusion means, this is from one modality, you have these features, and from the other modality you have these features, and let's say third modality is also there, and then you have some kind of combination combination mechanism, and then you have combined features. Then you feed this to a single model, which will give you the final decision. um, However, early fusion we have already discussed, okay, I won't repeat it. Yeah. um then we move on to the late fusion part. So what exactly is late fusion? Earlier you saw that the features were already combined, but now for the different modalities, let's say earlier we had this feature, right? Also we had this, and third we had this one. Now we want to combine, but not here. I will train i will train a model 1 for this modality, then a separate model for this modality, and third third model for this modality. Somehow it will give me some decision, and let's say this is D2, this is D1, and this is D3. Now we want to combine this D1, D2, D3 using some combination. We can say voting or averaging. We can use any of the techniques and then give the final decision. So each modality is having their own its own pipeline, and after everything is done we are combining just the decisions or the probabilities or the scores. Okay, it gives us more flexibility. I can use any model which is my favorite model. For let's say this is audio, so I can use any audio based model for this part. But in this case, in this early fusion case, the model is, so it designed for the combined modalities. ठीक है. Then we are talking about the, yeah, so which of the following is not a feature fusion technique? So early fusion, it is. Late fusion, of course. Decision fusion, same as late fusion. That means we are having some decisions from different pipelines and we are combining the decisions itself, not the features. This is also known as feature fusion. Okay, feature fusion, late fusion, decision fusion. So they are all valid methods, valid techniques. So selective fusion is not a feature fusion technique. Which of the following are true? The assumption behind early data fusion is the conditional independence between multiple modalities. Errors are uncorrelated during late fusion because errors from different models are handled independently. So early fusion, it makes an assumption. It makes an assumption that the modalities have conditional independence. We just discussed the conditional independence. It means that the two modalities are not unrelated. Let's say if there is happiness, I know that I am happy, then the smile and the tone of my voice will be somehow correlated. Whatever emotion I'm experiencing, it can be backtracked to somehow the modality, different modalities. And if I'm smiling, then my pitch and everything, it can be some having some kind of relationship between them. So they are not completely independent, they are conditionally independent. Independent, why do we call them independent if they are related? Independent means you can process them individually, and from one pipeline and one from the other pipeline, then you can choose independently without affecting like each other. If I'm processing the smiling part, it won't impact the other modality being processed. Let's say the transcript, they're unrelated in that sense, however they're not unrelated completely. Okay, so it applies to the early fusion. In early fusion, all modalities are combined at feature level, we know this. Now, from the late fusion, uh, errors are uncorrelated during late fusion. This is also true because in late fusion, if the every pipeline is independent, like every this is one pipeline, this is second pipeline. See, whenever we are training, this will also have some kind of error E1, this will have some kind of error E2, and we are combining this some kind of scores. Okay, but when we are training an ML model, you know, the back propagation and everything is happening, so this error will only be used for this model training, and this will only be used for this. So now E1 won't be responsible for model 2, and E2 won't be responsible for model 1, because it is concerned with only model 1 only. So only the corresponding error is used, so they are uncorrelated. Does not mean that whatever is happening in one pipeline will also happen in other pipeline. Yes, Shikha. Do you have any question? Okay, which type of questions can be asked in exams? See, last time I asked this question to one of the team member, like NPTEL team. So they just told me that the pattern will be same as the assignment questions, the quiz questions. Most likely it will be MCQ only. But if you still have any doubts, just to confirm, you should mail the support team and you can ask. Mostly it is going to be MCQs. जितना मुझे पता है it will be MCQs. Okay. Okay. So, next question is, feature selection tries to eliminate features which are descriptive, redundant, relevant, or interactive. So, feature selection means that we have, let's say, 100 features, and out of those 100 features we want to select some important ones. So feature selection algorithms are there, and they tell us how we can, which features are more responsible for the output. Okay. It wants to eliminate the redundant features. Redundant features provide redundant or overlapping information which may not contribute significantly, and they consume more resources and increase the complexity. So if we remove the redundant features, then model's complexity can be reduced. Okay. Let's say we have a data set of house price prediction, and we have various features. Let's say we have size of house, number of rooms, number of bathrooms, the distance वगैरह वगैरह, ऐसे बहुत सारे we have features. Let's say the size of house and the number of bedrooms are highly correlated, in the sense that, let's say, size is increasing, then number of bedrooms will be, there's high chance that it will be higher. Okay. So it will be correlated. But is it correlated with the other, let's say, distance to nearest school? No. Size of the house does not determine the distance to the nearest school, because they're not correlated. Okay. And similarly, this is also not correlated to the size of the house. However, the number of bedrooms, it might be the closest correlation. um, so we know that, like, if we go by common sense, then larger houses tend to have more bedrooms. So in this case, number of bedrooms feature is redundant, and we can remove it, and it provides similar information to the house. If you say 4 bhk or 3 bhk, it is highly likely that 2 bhk will have smaller area than 4 bhk. Okay. So kind of redundant. So we want to eliminate the features, this redundant feature. So this reduction can lead to better model performance and efficiency, and especially where we have noise or increased computational complexity without adding significant value to the predictions. So basically, to summarize, we have a lot of features in the beginning, but we want to know which features are actually essential. And how do we determine that? We will see in a while. Like, how do we know that which feature to keep and which to not to keep? Okay. This is, yeah. So the process of identifying, selecting most helpful features in a dataset, it is known as feature selection. In the ML pipeline, it is an essential stage, right? We should be concerned about feature selection. Why should we be concerned? uh, it Unnecessary features can lead to overfitting, poor training speed, poor model explainability. So firstly is poor generalization or overfitting. This is a common issue in machine learning when a model learns to fit the training data too closely, and it fails to generalize. If new data is shown in the form of test data or any external inference while we are doing it, I mean unseen data, you can say, then it performs very poor. Let's say on the training data it is giving 90% accuracy, but on the test set or on the unseen set, it is not able to give even 50%. That means there is a huge gap. The model is very specifically trained on your training set, so it can be called as overfitting, and it leads to poor performance on unseen data. um, if the number of features are increased, then overfitting is more likely to happen. Okay. And poor training speed, of course we need more resources, more compute power, more storage requirements. And so feature selection is more about improving model performance. So that is why we reduce the let's say initially it was 512 dimensional, now it has been reduced to 256. That means we have saved half of the memory, है ना? So it is half the size. So also the explainability part, that means देखो irrelevant information is also there. You will be confused, even the model will be confused which features to focus on. Let's say if in house price prediction, another feature comes as color of the walls, ठीक है? एंड मे बी ऐसा हो रहा है, मे बी इट इज़ द केस दैट दिस इज changing. Let's say yellow, pink, everything is happening, going on. um, the model is trying to predict this house prices, but is it a relevant feature? No, because color can be anything. It does not determine the quality of the paint. Can be still an, you know, good feature, I would say, the quality. But the color, exactly, it is not a good feature. So we can remove this feature from the feature set and then train the model. And if we, let's say, do not remove it, and if we want to say see why my model is giving this 8 lakh or 8 crore as the predicted price. So if you want to trace back and tell, like, dive deep into the model and explain where exactly what explainability is all about, okay? So it leads to poor model explainability, because the model will be very confused whether my decision was based on this feature or some other feature or color of the wall. So unnecessary information should be removed. So this is, all three are true. So it leads to poor generalization, poor training speed, and poor model explainability, okay? Okay, we begin CFS by calculating all pairwise correlation. Now this is interesting. CFS is basically feature selection, okay? So correlation based feature selection, and it calculates all pairwise correlations. The feature with a higher mean absolute correlation would be deleted if a pair of features correlation exceeds a predominant. So I will just explain it to you. Let's say we have feature 1, feature 2, feature 3, and feature 4. We want to see which features are redundant, or which can be removed, which are not important. So one way of doing that is, you understand correlation means how closely they are associated, how is one impacting other. If, let's say, f1 is increased, does f2 also increase? That means they are correlated, okay? They have some kind of relationship. Now what I can do is I can uh, calculate the correlation between f1 f2, f1 f3, f1 f4, then f2 f3, all possible pairs, ठीक है? f3 f4, f2 f4. So these are, let's say, all the possibilities to check whether the correlation is high or not. So let's say this correlation is, there is a score going on, so this gives us zero point 0.4, and this is 0.9, point 2.6, ठीक है, 0.1 and 0.8, something like that. So now what we can do is see, and let's say my threshold is 0.5, ठीक है? Anything which is having correlation more than 0.5, I will consider it as a redundant information. They do not have high correlation. That means they are important individually. I cannot just remove and the other and keep only one of these, ठीक है? So this is important for us. Similarly, we need to keep these. Then if f2 and f4 are having so much of high correlation, that means we can skip one feature out of this, and we can only keep only, let's say, f4 I'm keeping, so f2 I will discard, I won't use it. And f1 and f3 are highly correlated. ठीक है, so maybe I can keep only F3 and not F1. So uh, that is how we found that these are important, and we were able to eliminate the redundant information. Although I just oversimplified it, but this is just to give you an idea about how we do that. ठीक है, so correlation based feature selection, um, the primary goal is to select subsets of features that are highly correlated with the target variable and being uncorrelated with each other. And the feature also, one important thing, the decision, the why, that means why that we want to predict, it should be highly correlated to all of the features. Okay, it should somehow impact the features. So it calculates a merit score for each subset of features based on their correlation with the target variable and their intercorrelation, and the high merit scores are selected for the final subset. So this is something, a flow chart for this CFS. I hope it is visible. It was stuck. Okay, so let's read this again. We begin CFS by calculating all pairwise correlations, the feature with the high mean absolute correlation with other features. See, with other features would be deleted, which is true. And if a pair of feature correlation exceeds a predetermined threshold, मैंने बोला था कि 0.5 से ज़्यादा I will discard, so yeah, which is true. Okay, as opposed to treating each modality separately, affective stimuli should be classified simultaneously for all the available modalities. So treating each modality separately, does that make sense? Like it can be classified simultaneously using all available modalities. We call it as multimodal affective classification. We're talking about this since this lecture began. Now it helps us to improve the scores, and might help actually, and does not always guarantee increased accuracy. However, it can provide some good insights into the additional information. If we by chance we are able to obtain some complementary information, then it will enhance it as well. ठीक है, so okay, next is slow fusion eliminates the synchronization requirement while taking advantage of correlation between modalities. We just discussed that there is a third type. One is the early fusion, then comes the late fusion, and then one is intermediate fusion. This is the intermediate or slow. ठीक है, so intermediate में क्या होता है कि we combine it hierarchically, like we can say intermediate steps may we are combining the information instead of combining it at both the extremes. We are combining in somewhere in the middle of the pipeline. So we fuse this data in the form of a high level representation or the latent representation. Then latent representation is fused. So let's say we obtain some new representation, जैसे कि I, oh my bad, so I drew this. This is kind of a latent, you can say, vector or representation. Okay, because initially it was a video like this, and now I have processed it and obtained a latent representation. Similarly, for other modality, this is, let's say, the audio, and it is also having some kind of representation, and then we are combining the latents with each other. We can add it, we can concat it, we can do anything. We can use attention mechanisms, so different techniques are available. Okay, I think there should be a diagram. I will show it to you. So it is more of a balanced mix. Early fusion requires early concatenation or fusion of the features at very early stage. And we also require synchronization is a main problem with early fusion. Late fusion, problem with late fusion is it is very simple although, but then the problem is that we miss out on the correlations between the data. Now this slow fusion, it combines the benefit of both. It can use lesser requirement for synchronization, but then also it is, since it is combining the information from both the modalities at some intermediate stages, it requires slightly less synchronization, whereas it also is able to capture the correlations. So yeah, this is the case. So if there is only one modality, the single frame, or you can say, let's say, treat this as modality, okay, this one is one modality. So let's say you're combining information from two sources. This is just one source, okay, one modality, then becomes two modalities. So one is this one is this one. You're processing them separately and then you're combining it here later in the pipeline. Then it is the early fusion case where the combination is happening here. All the modalities are being combined initially and then only a single pipeline is there and then it gives the final decision. Now slow fusion, if you see, it is more like a uh, this is a early fusion, similar to early fusion, right? But then we have different branches. This is a different branch, this is a different branch, right? There are four branches going on, then becomes two branches, then becomes single branch. So hierarchy is kind of going on, okay? So it is more of a intermediate fusion, intermediate method, you can say. So it eliminates the synchronization requirement, or it also takes advantage from the correlation between the modalities, okay? So the answer is true. Okay, real-time prediction from multimodal data stream requires larger window segments. True or false? Real-time prediction from multimodal data stream requires larger window segments. See, real-time means whenever you see this word anywhere in the questions, real time, that means live, something is live. So that means we need speed. Speed is the main concern, okay? So real time predictions, should we use larger window segments? Let's say there is a video going on, okay, or streaming is happening, then and you want to obtain the emotional information, okay, and a person is on a video call, let's say, and the system is determining what is the emotion being expressed. So let's say these are the windows, or this is the full video scenario. So are you going to take the short windows or larger windows? We are going to be, we expect more speeds. So do you think that these large windows can be processed in that time? No, because smaller windows are more like better in the sense that it will require less computational power. So less computational power means higher speed, right? Less data to process, less data to process means more speed. So real time should be, they usually what they do is often require smaller window segments rather than the larger one. What is the benefit of using the larger one? It provides us more context information. So provides more context information. Let's say I was smiling before and then I started laughing, or even let's say I was smiling, then I started crying. Then you will see that okay, certain emotion is being expressed here, which is not happiness, right? It's not, it might not be happiness, it might be something I can recall from my uh, experiences, or I just remembered something which disturbed me. Anything can be there. So it provides more context if we take larger window segments. And if we take just a small window, so it will just tell me, okay, you are smiling here and you are crying, so it will assign different labels to these two windows. However, through this it will provide a different label. So depends on your application. What this is a trade off, right? So you want to take as much as context as you can. However, it requires more compute. So it, in the real time, we want to reduce the latency, reduces the latency because smaller windows are being processed, and it makes it more suitable for real time applications. Okay, again, where timely responses are critical. Okay, you cannot just wait for like 5 minutes for your phone to unlock when you're using this facial recognition system. It should be real time, quick. So it requires smaller window segments. Okay. Okay, how much information each modality conveys about the expressed affect during multimodal interactions? It is determined by modality selection, feature selection, redundancy, all of the above. So how many modality should we choose, and how many which modality is contributing the most? There are some techniques you can like similar to feature extraction, you can say. Okay. uh, so in this case we are talking about, firstly we need to see the modality selection. um, Modality may we have, let's say, three branches, and the decision is happiness. So now you want to backtrack, you want to see which modality is the dominating one, which one is influencing my decision the most. Okay. And then feature selection is also there in, let's say, a feature such as eyebrow movements, lip curvature, or any other features, or audio features. Which features are the most important, you thought, in that pipeline? Then redundancy, we also want to know the redundant features so that we can remove it and make our model like better. um, so how much information each modality conveys it is determined by modality selection. I think it should be modality selection in my opinion, but others are not directly related to this, so we will check this out. However, in my opinion, it should be modality selection, of course, because we're just talking about the modality, right? Actually, feature selection can also be there, because let's say you have features like AU. In case of early fusion, it can be useful. So yeah, it can be actually useful. Let's say we have AU1, AU2, then we have this audio features, let's say MFCC. So this belongs to different modality, this is belonging to different modality. And if you analyze and trace back that which feature is the most important one, which is the most like contributing the most to your decision, let's say you figure out that this is a AU feature, that means the AU feature is very important, that means the visual modality is more important. We can also deduct, like do this we can reach this conclusion. uh, so visual modality is the more dominating one, and more like it decides the final label. Okay, what is the primary objective of combining multiple streams of data in an emotion recognition system, which is exactly the multimodal affect systems, right? So, what is the primary objective of this? Decreasing computational load? No, because ultimately, if you're adding more data, it increases computational load. Okay. Second is enhancing accuracy with complementary information, which is correct. C is simplifying the analysis process. No, if you use only one modality, that would be more simple. Instead of using three modalities, it will be more complex, right? Then reducing redundancy in data. um, no, because redundancy is like caused by adding more modalities. So we want to, so our goal is to reduce redundancy. However, if we add more modalities, it will introduce some kind of redundancy, so this is incorrect. So the correct answer is B. Okay, these slides will be available, so if you want to go through the content, you can go through it later. uh, okay, what is crucial with respect to different modalities in multimodal systems? Increasing the number of sensors, understanding the temporal synchronization, implementing complex fusion methods, reducing the size of affective corpora. What is crucial with respect to different modalities? So as we discussed, like if we are combining multiple modalities, one of the major concerns is the temporal synchronization. That means, let's say, you're capturing video, so video may usually the typical sampling rate, or sampling rate, you understand, whenever we read a data point from that stream, okay? So after every, let's say, 1 second, let's say after every 1 second you're reading one video frame, so you're capturing the, you're saving a frame, let's say up, it's more like a screenshot, okay? What is happening at, this is the time axis, okay? Time is passing. So at 4 o'clock, let's say, this was happening, then 4 5 p.m. the person kind of moved here, okay? So this changed, then I'm taking another reading at 5:10. So every 5 minutes I'm taking a reading, that is called a sampling part, okay? Sampling rate means how many samples are you obtaining in 1 second, okay? So somehow I'm taking these readings, and for the sound I'm taking, let's say, five samples every 30 seconds I'm taking. So 1 2 3 4 5 6, like I'm taking so many samples for the audio. So audio is having higher sampling rate, okay? So it is taking, so how are you going to combine this information with this information when this is not aligned, okay? You have only, here I showed you at the timestamp, but initially, let's say we only have 10 frames, but so 10 video frames are there and 100 audio points. So how will you combine this? You cannot just like divide by 10 or do something like, so any technique would be required to handle the temporal synchronization part, okay? um it refers actually to, it refers to aligning the data samples from different modalities so they're corresponding to the same data points. um, I'm taking some reading from audio and video, so it should be from the same timestamp, it should be same 4 p.m. only. So this should be from 4 p.m. Let's say this person was saying hey there, some point is it, so it should be from the same point. It shouldn't be the case like I'm taking the frame from 5 p.m. and then audio is from 4 p.m. It won't be, the correlation will be less, because this is from different time altogether. So we need synchronization, and without proper synchronization the data might not accurately capture the same events or time periods, leading to inconsistencies and inaccuracies in the analysis. So understanding temporal synchronization is the most important out of these. Okay, थोड़ा सा different question है. What is the primary goal of projecting the data into a higher dimensional space in multimodal effect? Even in we're just, the question is about multimodal effect recognition, but instead, um, this question is valid for many, like this is a very generic question. Why do we even want to transform our data into higher dimensional data? um, do you want to increase the computational complexity? Of course no, because who wants more complexity? We want simple pipelines as much as possible. We want simple representations. Everybody wants simplicity, not complexity. to reduce the amount of data. No, in higher dimension, how is the data being reduced? I don't understand, so this option is also incorrect. To enhance feature representation, um, this is the correct answer. We'll see how. And to standardize feature representations, see, different modalities carry different information, so we cannot just expect that everything is on the same page. We need to take care of the synchronization, we need to care of the normalization, but then we cannot standardize everything, that it should be on the same page. So the better answer would be to enhance feature representation. So advantage of high dimensionality, it lies in the fact that it is able to capture more detailed information about the data. Okay, it enhances the feature representation. It becomes possible to capture more complex relationships. Okay, let's say, I'll give you an example. One person is standing here, and let's say you're looking from satellite, and you're looking at this point. Okay, and you see that there is a building. Okay, and you see this is the people are standing here. But if you use 3D space, if you use 3D space to represent this, then you might see that, okay, one person was here, and this person, like this and this person, one is here and one is here. Maybe that from the top view it's looking that they're on the same point, but the height is different. Like maybe one person is on first floor and this person is on fifth floor, but if you look from top, the location is the same. Okay, so how did I get to know the difference? I projected into a higher dimensional space. So sometimes higher dimensional, it is an advantage that we are able to capture the complexities that we are missing out here. We don't know, we are able to capture that, okay, this person is in a different building, but these two are in same building, they're overlapping. But then in the within the building where those people are there, we have the coordinates, so we could plot it 3D plot as compared to 2D. So now I think they're more separable, you can see. So another example can be, if it is 2D, then you can see that this is not separable. This is kind of the top view. If you take this and see from here, look down, then it would be looking something like this. Okay, and if you want to make it separable, maybe the boundary will be something like this, but not a linear one. But here, if you see, a linear boundary can also work in a higher dimensional space. Okay, it becomes more separable. Same, the height difference. Okay, so we want to enhance the feature representation. Okay, which challenges arise when performing early fusion with features? So, lack of synchronization, inconsistent feature extraction techniques, dimensionality reduction, feature normalization. Lack of synchronization is there. This is a challenge. We want to make the modalities synchronized with each other. So first one is true. Second is inconsistent feature extraction techniques. This is also true because the method of obtaining data for each modality is very different. Okay, so it can lead to inconsistencies in how features are represented. Let's say your text is more on the linguistic side, but then your visual features are more on the facial expressions, AUs, action units, more on the spatial domain, right? So one another can be in the temporal domain. So might be some inconsistencies in between. Then comes the dimensionality reduction part. It can be a challenge in fusion. It's not specifically related to different like it is not that issue that the curse of dimensionalities of course is there if we do not remove the extra dimensions or the useless dimensions. Okay, feature normalization. normalization is very important. ठीक है, and it is not necessary for early fusion. These challenges are very standard across different algorithms. So in this case, they say that, okay, this is answer 1, 2 and 3. I think 1, 2, 3 and 4 can also be there. This is definitely a challenge. One is there. Inconsistent feature extraction technique, this is also there, we need to handle that. Dimensionality reduction means the curse of dimensionality can be there, right? This is also true. Feature normalization, it's not a challenge. Maybe we can just use the like mean and the standard deviation, okay, to normalize data. It's not specific to early fusion or something, it has nothing to do with fusion. But I think normalization is independent. It is more independent of this fusion process, okay. So that is why I think this is correct only. 1, 2 and 3. Feature normalization is more like कि one value is in 100 and then other is 50, and then this is, so I want to scale this down into 0 to 1. So maybe this will become 2, 5 and like, okay, maybe 0.2, 0.5 and 1, something like that. 1.0. So this becomes in the range of 0 to 1. This is more like a normalization thing. However, it is not specific to feature fusion. Feature fusion may, we will just, this is independent one feature, and then another feature can also be normalized. So it's not that of a challenge. Okay. Soft fusion and hard fusion. Soft fusion, we have seen that, okay, did we discuss the soft fusion thing? Soft fusion is basically when there are some kind of confidence values are associated, and hard fusion is when you say, in the case of late fusion na, so we have one pipeline, two pipeline and three pipeline, and it will, let's say this is giving happiness, happiness and sadness. Now how to combine these labels to find the final label, right? So there are multiple strategies. One can be let's say averaging or something. So soft fusion, what it does is it assigns a confidence score. Let's say it will say 0.7, I think it is the happiness, okay, and 0.3 sadness, maybe probability or some score like that. And hard fusion will be, so it will, let's say, give some weightage to this these different labels, okay. And then like w1 x1 plus w2 x2, so weighted summation can be done to obtain the final score, okay. And in the case of hard fusion, if it is saying like and, so and means everyone should agree, only then the label will be assigned, okay, otherwise there will be some kind of ambiguity. And in case of or means if only one, even one is saying happiness, then it is more like I will say that the label is happiness, okay. So examples we can see. So soft fusion involves combining decisions from multiple modalities using measures of confidence or probabilities associated with the each of the decision. The output from each modality's classifier is accompanied by a confidence score. Let's say the first facial expression tells you I'm 90% sure that this is happiness. Then these indicating the classifier's level of certainty about the decision. Now the confidence scores are then used to weigh the contributions of each modality. Again, same thing. If one model is more confident, one facial expression model is saying I'm 90% sure, and audio model is saying I'm to, let's say, 1% sure, then that means more priority will be given to facial expressions. So yeah, again, let's say person is speaking, the facial expressions tells happy with the confidence of 80%, and the speech classifier with predicts neutral with 60%. So more weightage will be given to the higher weight to the facial expressions because the confidence is high, okay, resulting in a decision of happy with an overall confidence level which reflects the combined certainty. And in case of hard fusion, as I mentioned, directly it is combining, it is not taking into consideration any kind of scores. So let's say facial expression and speech analysis. Suppose the facial expression predicts happy and the speech predicts sad. So in hard fusion, any only one like outcome will be there, and it's kind of a boolean thing. Okay, and if we use or, then this decision might be happy if one modality predicts and ignores the other prediction. And if it is using and operation, then both need to be on the same page, same decision, in order to uh, the emotion to be accepted. So both modality to agree on the emotion for it to be accepted, and potentially resulting in a neutral or inconclusive. Means uh, like, if let's say three of them are saying happiness, that means true label will be happiness. But then if one is saying sadness, then it won't give any result. It will say I'm not sure. ठीक है, तो I'm not sure means it won't give us a decision. So this is hard fusion, and then it is, the other one was soft fusion. So let's read these statements out. Soft fusion combines decisions using measures of confidence, which is true. ठीक है. Hard fusion uses logical operations and or. So this is also true. Third is soft fusion combines vector directly. No, hard fusion जो होती है that combines feature directly, while hard fusion uses statistical analysis. This is exactly the opposite. So 1 and 2 are correct, but third one is wrong. So B is correct. Then adding and removing modalities is easier in early fusion. Okay, this question is very important, very interesting and very important. So I would say that please pay attention to this one. In early fusion, we are kind of combining. Let's say one is concatenation, right? So one method is, so let's say this was 64 and this was also 64. So now we get 128 dimensional vector. This is just concatenation. Another thing can be addition. Okay, if we have same dimensions, so we can add it and it will give us only a new vector, which is the summation of this these two modalities. So it will be a new addition wala vector. Now the model in this pipeline, it is trained on this particular model, is already trained. ठीक है. Model, what is the input to this model? Combined from M1 and M2. M1 is this, let's say one modality 1, modality 2. Okay, now comes into picture another modality, M3. M3 is there, you have the data you want to combine. Let's say in this case, if you want to add, it is still fine, you can add all three. ठीक है, you can add, इसको भी add कर दिया, it will be giving some output. In this case it's fine, but in concatenation the model is already training on something which is 128 dimensional. It is trained. Now if you want to concatenate, it will be 64 into 3, मतलब 128 में भी 64 ऐड कर दिया. ठीक है, तो इतने डायमेंशन हो जाएगा. So this is 192 dimensional. ठीक है, 192 dimensional, but the model needs 128 dimensional as input, so you cannot add another modality in this case. ठीक है. In early fusion, in late fusion what will happen? This is one modality, this is the M1 original. ठीक है, this is this is M2, and this becomes M3, new one. So initially also they had their own models. So this one has this own model which is independent from others. So it is just giving decision number 1, this is giving decision number, this is one model 2, decision 2, right? And similarly for this it gives decision 3. Now if you want to, initially we were combining this information by taking voting or majority, ठीक है, like that, maybe and or whatever. So does it matter how many branches do you have in this case? It is relatively much easier to incorporate, to add or even remove. If you want to remove d1, just remove it from the pipeline, but here if you want to remove d1, the model is already trained to do so, so you cannot remove directly, okay? So this is false. So it is not easier, it is tougher. Easier in the case of late fusion because more independent pipeline, ठीक है? Okay, next question is what is the primary focus of the Simane dataset? Simane dataset है, it is a dataset which is made for human computer interaction purposes and particularly for affective computing. It contains videos, okay, videos capturing audio visual interaction, means your face and your voice is also being recorded between a human and an operator. Operator is a avatar, an avatar with 4 personalities. There are these are the name of the personality. So different avatar is there. So let's say here you can see all the avatars are there. This is 1 2 3, okay? So I think this is Poppy, no, okay, Poppy, Obadia, Spike, and Prudence. So yeah, they have their names. These are the four types of personalities or avatars that are there. And this is the detail, like the 25 fps and correlation, I'm sorry, correlation nahi, it consists of audio visual interaction, human and operator, ठीक है, and it undertaking the role of an agent. Now it annotation में क्या है, what are the annotations? It gives us the states, some states like agreement, interested, certain, concentration, thoughtful, and continuous ratings are there. Also some emotional ratings are also there. So but what is the primary focus? If we talk about the focus, then is it collecting textual data? No. Creating virtual agents for gaming? No, actually this is for the emotional. Since we are talking about affective, it is more of a emotional responses through dialogue interactions, okay? Why do we need to include different personalities? Because then the system will be more robust, depends on your personality traits as well. Analyzing physiological signals? No. So third is correct. Okay, what trade-off is involved in choosing the duration of data segments for affect prediction? I just told you that the window size, if it is larger, then more context can be captured, but if it is shorter, then it is fast. Okay, so this is more context. The trade-off between physical activity and conversation? No. The trade-off between real-time analysis and computational resources, hardware costs and system performance, or user comfort and data accuracy. So we know that if we are talking about the real-world analysis, real-time analysis and the computational resources, if even in real time we have more computational resources, we can use more, I mean larger windows, right? So this is a trade-off. So option B is correct. Okay? So yeah, longer windows can capture more context but need more resources. Short ones are quick and more suitable for real time. uh Dhanya, do you have any question?
Yes, I'm sorry to disturb, ma'am. Like, how many more questions? Just for an idea.
Yeah, I mean, four to five questions. I'm just doing it very
Okay.
fast. Yeah, yeah. We will end in a while. Okay,
So,
so
could you please say where are the videos uploaded?
sorry.
Where are the videos uploaded?
I didn't catch you.
Where are the videos uploaded, ma'am?
Okay, videos. So I think the channel link should be shared with you by now. You can ask the NPTEL team. It is, if you search on even YouTube, you can search for Affective Computing live sessions, and there will be my channel, Akanksha. So uh, you can just go and check it out. The playlist is this Affective Computing CS04, so you can
Okay,
find the
ma'am.
playlist. Okay. Okay. So I'll just complete this quickly. So frequency is more, in that sense, a more computational. So anyways, it is a trade-off between this larger window size and smaller window size and the computational resources, basically. Okay, so this is the trade-off. So what is the significance of considering longer windows? Longer windows provide more temporal data, right, allowing for better prediction accuracy. Reduce, this is incorrect. And it capture only the onset of expressions, no. And longer windows in fewer frames, no. So the first option is correct. Longer windows provide more temporal data, this increases. And no, this is shorter windows can only capture the onset and leading to less accurate, like that. Longer windows in more frames, okay. So this is a trade off. In which scenario would the cost of an incorrect prediction will be higher in multimodal? See, whenever we talk about the cost, even if my facial recognition, my device will fail to recognize me once in a while, then it will be not a problem for me. But if it is a very sensitive case, let's say medical analysis, medical domain, something related to, like, let's say this is just monitoring, even if it is, the model is wrong, it is fine. Suggesting movie, it's okay. Analyzing sentiment is also fine. But then if you want to do something related to therapy, mental health, or even physical health in certain manner, then it becomes very crucial for us to, every incorrect prediction is very expensive. Okay, and I'm not talking about the cost, but expensive in terms of wrong information, wrong diagnosis, uh, wrong, maybe false positives, false negatives. So it is very sensitive in the case of healthcare, and even some uh, sensitive, let's say, security related applications, so like that. Okay. Okay, how many different personalities does the virtual avatar have? We just saw there are four different personalities. One is Prudence, Poppy, Spike, Obadia. This is just a factual question, and every avatar, every this virtual avatar is having different characteristics, different behavior. Okay, so there are four. Then comes what dimensions were annotated. As I mentioned, some emotional labels were there. So for that, they used this four labels. One is arousal and balance, we already know, right? And expectation and power, that means the anticipation is the expectations, and it captures the level of anticipation or readiness for something to happen. And power is the degree of control or dominance. So dominance is also familiar. Okay, only the expectation is a different annotation here. Okay, so four total. The first option is correct. Then one of the main challenges faced by emotive challenge. Emotive is more in the wild challenge. So in the wild means it is not collected from the uh, in a setup, in a laboratory setting. It's more randomized. So it means randomized. So randomized data sets always have more diversity and more variance. Like even let's say some happiness. So if you tell person that you have to pretend to be happy, everyone will just smile. But if it is a real world, then one person's happiness might be different from other person's way of showing that. So in that case, the main challenge becomes, is it the limited computational resources? No. So you can see, like, these engagement, some people are engaged, some are not. You can clearly see in some cases, but in some cases you might not be able to see. The same class they belong, but there is a variability, right? Same label but different looking. So the main challenge is intra class, matlab within the same class variability is high. If it is just a straight up smile, I can say everyone is happy. But it is much more complex in the case of in the wild data sets. So limited computational resources, no. Lack of diversity, no, it is very diverse. Overfitting, no. Intra class variability due to varied environments, this is the correct answer. And which of the datasets is used for multimodal affect specifically for sensors data? This Till now we have discussed two datasets. One is Simane dataset, another is emotive. Okay, this is more of a in the wild. And emotional labeling, this is also the other one. This is more on the audio or emotions, like speech emotion recognition. Okay. And then comes the dataset which is ascertain. The full form is a multi-model database for implicit personality and affect recognition. So it contains big five, there are five personality traits, and the different sensors are there. So EEG readings, ECG readings, GSR, etc. And it has all of the data. Now a certain data sets, it has these. You can refer to this later as well. Affective ratings, physiological responses, personality traits. So these three things they have taken care of for 58 users, 36 videos. Okay, so the answer is ascertain. This is related to the sensors data. Okay. Okay, finally we come to the end of this session. I know it kind of went long. So yeah, the next session will be 25th March. And if you have any doubts, you can please unmute, or if you, you can also type this in the chat box. Otherwise, we'll meet in the next session. So, are you having any doubts?
Thank you, ma'am.
Okay, so I think we do not have any doubts. So we can just
No, ma'am.
okay, thank you. We will end the session now, and I'll see you guys in the next session. So I had to rush through this session. uh, Sorry for the, we could skip some questions, but I just wanted to cover everything. So if you have any doubts, you can refer to the slides, and I think everything is mentioned in the slides very clearly. So I put so much content for your reference. So I think that would be very helpful. uh, okay, on that note, we should I think we should end the session. Thanks for joining once again, and I'll see you in the next session then.